Okay, here's a thought. What if you could solve problems that right now would take even the biggest supercomputers, like millions of years? And what if you could design medicines perfectly tailored to your own body? Or, I don't know, create materials we can only dream about today? Or even make communications genuinely, truly unbreakable? It sounds like science fiction, right? A computer that doesn't just do things faster, but thinks differently. Right, so let's try and unpack this a bit. Today we're doing a deep dive into, well, the really groundbreaking world of quantum computing. We've got some incredible source material you sent over, articles, research papers, your notes, and our mission really is to cut through, let's face it, pretty dense jargon. We want to pull out the most important stuff, the key insights, and hopefully give you those aha moments so you feel properly clued in on this transformative field.
Yeah, and that's a really key point you made right at the start, because this isn't just, making today's computers faster. It's not just a bigger supercomputer. Quantum computing is a completely different way of doing computation. It's based on the rules of quantum mechanics, which are famously weird, but also incredibly powerful. And the absolute heart of it is the quantum bit, or the qubit.
Qubit, right.
Now, we all know classical bits, they're simple, either a 0 or a 1. Like a light switch, it's on or off, that's it. But a qubit, well, a qubit can be in what's called a superposition. It can be a 0 and a 1 at the exact same time.
Both simultaneously. How does that work?
Just think of it like spinning a coin. While it's spinning in the air before it lands, is it heads or tails?
Neither, or both.
Exactly. In a quantum sense, it's in a state of being both heads and tails until you measure it and until it lands. That's kind of like superposition, but, the magic doesn't stop there. There are other really strange quantum effects that these computers use, things like entanglement and quantum interference.
Entanglement.
Correct.
That's the spooky action at a distance thing Einstein talked about, right?
That's the one. Yeah, it's where two or more qubits become linked, like deeply connected. If you measure one, you instantly know something about the other, no matter how far apart they are. Miles, light years, it doesn't matter.
Wow.
And then you've got quantum interference. It's basically how the probabilities of the different qubit states can add up or cancel each other out. It helps guide the computation towards the right answer and sort of suppresses the wrong ones. And what's truly fascinating, what gives quantum computers their power, is using all these things together: superposition, entanglement, interference. It lets them explore this just vast number of possibilities all at once. Think of it as massive parallel processing, but on a whole different level. And that's why they can tackle certain problems, not all problems, mind you, but specific, really hard ones that would take classical computers literally millions or even billions of years to crack. So it's not just faster, it's fundamentally different. It's a new paradigm.
Okay, that fundamental difference.
Yeah.
That's where it gets really interesting, I think. Let's pivot from the theory, the mind-bending physics, to what this actually means. What are the applications? Because this isn't just lab work anymore, is it? It feels like it's starting to touch real-world challenges, or it's about to. And maybe the most talked about area, certainly the one that grabs headlines, is cybersecurity. It seems like a real double-edged sword there.
It absolutely is. A double-edged sword is the perfect way to put it. You see, our entire modern digital security infrastructure, things like RSA and ECC encryption that protects your online banking, your emails, your company's data, they rely on one core assumption.
Which is?
That certain mathematical problems are just too hard for current computers to solve in a practical amount of time, specifically factoring very, very large numbers into their primes.
Right, I've heard of that. It's like a mathematical lock.
Exactly. A lock that even the fastest supercomputers today just can't pick efficiently. But quantum computers, they change the game completely. There's this algorithm, Shor's algorithm, developed way back in 1994 by Peter Shor, that's specifically designed to run on a quantum computer. And it can solve that exact factoring problem exponentially faster. Not just a bit faster, exponentially faster. It exploits quantum mechanics to essentially check all the possibilities at once.
So a powerful enough quantum computer could basically break all current encryption, just like that.
In theory, yes. A large-scale, fault-tolerant quantum computer running Shor's algorithm could render RSA and ECC totally useless. And the implication for you, for everyone, is huge. Any data that's encrypted now using these methods, emails, financial records, state secrets, could potentially be recorded today and decrypted later once those powerful quantum computers exist.
That's the store now, decrypt later threat. That sounds pretty scary.
It is a serious concern, definitely.
But, okay, it can't be all bad news, surely. You said it's a double-edged sword. So if quantum breaks encryption, can it also fix it?
Yes, exactly. That's the other edge of the sword. Quantum mechanics also gives us tools to create fundamentally new and theoretically much stronger forms of encryption. Quantum cryptography. The most prominent example is quantum key distribution, or QKD.
QKD, okay, how does that work?
It uses quantum principles, like the properties of single photons, to generate and share encryption keys between two parties. The crucial part is this. The very act of someone trying to eavesdrop on that quantum channel, trying to intercept the key, inevitably disturbs the quantum states of the photons.
It leaves a trace.
A detectable trace, yes. It's baked into the physics. Any eavesdropping attempt immediately introduces errors that the legitimate users can detect. They know someone's listening in, so they can discard that key and start over. It's like having a tamper-proof seal built by nature.
That's incredible. Is this actually being used, or is it still theoretical?
Oh, it's moving beyond theory. There are established protocols like the BB84 protocol, which is kind of the classic example using photon polarization. And we're seeing real-world deployments. People are building QKD networks over fiber optics, although distance is a bit of a challenge there. But now we're even seeing satellite-based QKD systems. China launched a satellite, QESS, specifically for quantum experiments, including long-distance QKD. That overcomes the distance limits.
Wow. Satellite QKD.
And it gets even more advanced. There's work on device-independent QKD, which aims to provide security even if you don't fully trust the QKD hardware devices themselves. It relies on testing fundamental aspects of quantum mechanics, like Bell's inequalities.
So trust the physics, not the box.
Essentially, yes. And one last piece of the puzzle. For any encryption to be strong, you need truly random numbers to generate the keys. Classical computers are deterministic. They can only generate pseudo-random numbers. But quantum phenomena are inherently random. So quantum random number generators, QRNGs, can produce genuinely unpredictable sequences. That's vital for top-tier security.
So quantum is both the potential code breaker and the key to unbreakable codes. Fascinating.
It really is. It forces a complete rethink of cybersecurity.
Okay, so from the digital world of security, let's shift to something maybe more tangible, more personal, our health. How is quantum computing expected to impact medicine and drug discovery?
Right. This is another area where the potential is just immense, truly transformative. Think about how we discover new drugs now. It's an incredibly long, complex, and eye-wateringly expensive process. Often takes more than a decade, costs billions of dollars.
Why does it take so long?
A huge bottleneck is understanding how potential drug molecules will actually interact with targets in our bodies, like proteins. Simulating these complex molecular interactions accurately is incredibly difficult for classical computers. Molecules are quantum systems, fundamentally. Classical computers can only approximate their behavior, especially for larger molecules. The computational power required just explodes.
So scientists have to rely on approximations and then lots of slow, expensive lab experiments, trial and error.
A lot of trial and error, yes. It's like searching for a very specific key for a very complex lock in a massive warehouse full of keys, but you can only try one key at a time, and your map is only approximate. Quantum computing changes that because it operates using the same quantum rules that govern the molecules themselves. It can simulate these interactions with unprecedented precision.
So it's like having a perfect map of the warehouse and being able to check all the keys at once.
That's a great analogy. Quantum algorithms like VQE, variational quantum eigensolver, and QAOA, quantum approximate optimization algorithm, are being developed specifically for this. They allow scientists to calculate the electronic structure and energy states of molecules much more accurately and efficiently. This could drastically shorten the research and development time, maybe cutting years off the process, and significantly reduce the costs. It helps identify the most promising drug candidates much earlier, reducing the need for so many failed lab experiments.
Are companies actually doing this now?
Yes, major pharmaceutical companies like Pfizer, Merck, Roche, they're all exploring this. They're collaborating with quantum computing firms and research groups. The early results are looking very promising, particularly in areas like accurately predicting how strongly a potential drug molecule will bind to its target protein, which is crucial for effectiveness. It's moving from approximation towards true simulation.
Okay, so discovering new drugs faster. That's huge. But what about making treatments more effective for individuals? You hear a lot about personalized medicine.
Absolutely. Personalized medicine is another key area. The idea is to tailor treatments based on an individual's unique genetic, makeup, lifestyle, environment.
But that means dealing with enormous amounts of data, right?
Yeah.
Genetic data alone is massive.
Exactly. Analyzing these huge, complex data sets to find meaningful patterns, correlations between genes, disease susceptibility, drug response is a massive computational challenge for classical computers. Quantum computers, especially with quantum machine learning algorithms, are perfectly suited for this kind of pattern recognition in vast data
I
sets.
thought so.
They can potentially identify subtle correlations and anomalies in genetic data much faster and more effectively than classical methods. This is vital for understanding the specific genetic roots of complex diseases. Think about genome-wide association studies, or GWS. These look for tiny variations in DNA across many people to see if they're linked to a particular disease. Quantum-enhanced machine learning could supercharge these studies.
Making it easier to find those links for diseases like cancer or Alzheimer's or diabetes.
Precisely. And importantly, it could help predict how you, specifically, might respond to a particular drug based on your genetic profile.
So the real benefit for the listener, for you, is the potential for treatments designed just for your biology. Fewer side effects, better results.
That's the ultimate goal, yes. Moving away from the one-size-fits-all approach towards truly individualized therapies, it could revolutionize treatment outcomes.
Okay, that's incredibly promising. Now, you mentioned proteins earlier, how drugs interact with them. I know protein folding is a huge challenge in biology, too. Is that something quantum can help with?
Oh, absolutely. Protein folding is one of the most fundamental and, frankly, most difficult problems in biology and biochemistry. Proteins are like the workhorses of our cells. They do almost everything. But they only function correctly when they fold into a very specific, complex 3D shape.
And if they fold wrong?
If they misfold, it can lead to all sorts of serious diseases. We're talking Alzheimer's, Parkinson's, cystic fibrosis, many others are linked to misfolded proteins. The challenge is the number of possible ways a protein could fold, even a small one, is astronomically large. It's just mind-boggling.
So classical computers struggled to figure out the correct shape, even things like AlphaFold.
Even incredibly powerful AI like AlphaFold, which has made amazing progress, still faces limitations. Simulating the actual folding process, the dynamics and the energy landscape involved, is computationally incredibly intensive. Quantum computers offer a different approach. Because proteins operate at the quantum-level interactions between atoms, electrons' quantum computers are naturally suited to simulating them accurately. They can model the quantum interactions involved in the folding process and calculate the energy states of different configurations much more efficiently.
Helping predict the final correct folded structure.
Exactly. And understanding how proteins fold and misfold is critical for designing drugs that can perhaps correct misfolding or target the specific proteins involved in disease.
And this isn't just for medicine, right? Understanding proteins could have other applications.
Definitely. If we can design proteins with specific functions, imagine creating novel enzymes for industrial processes, maybe making biofuels more efficiently, or developing new biodegradable plastics, or even enzymes that can break down environmental pollutants. It's foundational science with really broad potential impact.
It's amazing how interconnected all this is. Okay, so healthcare looks set for a major shakeup. What about another huge area? Artificial intelligence and machine learning. How does quantum fit in there?
AI and ML are fundamentally about finding patterns and making predictions based on data, and often this involves solving really complex optimization problems.
Optimization like
Yeah.
finding the best settings for the AI model.
Exactly. Training a deep neural network, for example, involves tuning potentially billions of parameters to minimize errors. That's a huge optimization task. Or selecting the best hyperparameters for a model. Classical computers can do this, obviously, but they can sometimes get stuck in suboptimal solutions, or it can take a very long time, especially as the problems get bigger and more complex, higher dimensional spaces, as we say.
And quantum can do better.
Quantum algorithms like QAOA, which we mentioned for drug discovery, and others like Grover Adaptive Search, are inherently good at exploring vast solution spaces simultaneously. They have the potential to find better solutions faster.
So faster training for AI. Better AI.
Potentially, yes. This could lead to more powerful AI models developed more quickly, and the applications are everywhere. Think about optimizing financial investment portfolios in real time, which we touched on, or streamlining incredibly complex global supply chains, or optimizing routes for thousands of delivery trucks dynamically. Quantum optimization could make these systems much more efficient.
Right, that makes sense. And what about just analyzing the data itself? AI needs data. mountains of it.
Absolutely. And the sheer volume of data being generated today is staggering. Quantum machine learning, or QML, offers new algorithms specifically designed to handle these massive data sets more effectively. Algorithms like quantum support vector machines, QSVM, or quantum principal component analysis, QPCA, could potentially perform tasks like pattern recognition or reducing the dimensionality of data much faster than classical algorithms.
Dimensionality reduction, like finding the most important features in the data.
Exactly, helping to cut through the noise and find the signal more quickly. The impact could be significant in areas needing real-time analysis. Think healthcare again, spotting disease outbreaks faster from patient data, or energy optimizing power grid distribution second by second, or autonomous vehicles processing sensor data instantly for safer driving, even climate modeling, handling those huge, complex data sets.
Okay, so faster optimization, faster data analysis. What about understanding language? Natural language processing, NLP. That seems like a very human skill.
It is, and classical NLP has made huge strides. But understanding the deep meaning, the context, the nuance of human language is still incredibly challenging for computers. Quantum NLP is an emerging field exploring new ways to represent language. Some approaches use tensor networks and quantum principles to potentially capture semantic meaning and contextual relationships more effectively than classical models.
So AI that really understands what you're saying.
That's the hope. It could lead to much better machine translation that gets the cultural nuances right. Virtual assistants like Siri or Alexa that are truly conversational and understand intent, not just keywords. Or tools that can accurately summarize complex documents or answer intricate questions from text much more effectively. It's about making human-computer interaction feel more natural, more intelligent.
Okay, the synergy between quantum and AI seems incredibly powerful. Let's shift gears again. What about finance? That's an industry built on speed and data analysis.
Finance is definitely one of the sectors paying very close attention to quantum computing. The potential advantages are just too significant to ignore. Take portfolio optimization. The goal is always to maximize returns while minimizing risk, choosing the right mix of assets. With thousands of potential assets and constantly shifting market conditions, this is a massively complex calculation.
Too complex for classical computers to find the absolute best answer quickly.
Often, yes, they have to use approximations or heuristics. Quantum algorithms, again, like QAOA or VQE, can explore that huge space of possible portfolios simultaneously. They have the potential to identify truly optimal or near-optimal asset allocations much faster and potentially more accurately than classical methods.
Meaning portfolio managers could react almost instantly to market changes.
Exactly. Imagine recalibrating a complex portfolio strategy not overnight or in hours, but in seconds. That provides a huge competitive edge. And we know major players like JPMorgan Chase, Goldman Sachs, and others are actively researching this. They're exploring quantum for asset allocation, finding arbitrage opportunities, improving market predictions. It's a race for quantum advantage in finance.
Makes sense. And what about the flip side, managing risk? Markets are volatile.
Risk analysis is another critical area. Accurately modeling market volatility, credit risk, systemic risk across the interconnected global financial system. It's incredibly complex. You need to process vast amounts of data and model complex interactions. Quantum-enhanced models, perhaps using techniques like quantum Monte Carlo simulations, could potentially process this data and model these systems with greater accuracy and speed. They might be able to identify subtle correlations or potential contagion effects that classical models miss.
So for the average person, this means maybe a more stable financial system, better protection against crashes.
Potentially, yes. More robust stress testing of banks and financial systems, better insights into vulnerabilities before they become critical, allowing for proactive measures to mitigate threats. It contributes to overall financial stability.
And within finance, there's always the problem of fraud. Can quantum help there too?
Yes, fraud detection is essentially a pattern recognition problem in massive data sets. Financial transactions generate astronomical amounts of data. Finding the tiny signals of fraud amidst all that noise is tough. Quantum-enhanced machine learning, using algorithms like QSVM or quantum clustering techniques, could potentially analyze transaction data at much higher speeds, identifying subtle anomalies or suspicious patterns indicative of fraud in near real time.
Catching fraud faster, protecting consumers and institutions.
Exactly. It helps safeguard trust in the financial system and prevent significant losses for everyone involved.
Okay, finance is clearly a big one. Let's move to the physical world, supply chains and logistics, getting things from A to B efficiently.
Right. Another area heavy on optimization. The classic example here is the traveling salesman problem, the TSP.
Ah, yes, find the shortest route connecting a bunch of cities, visiting each one only once.
Simple to state, incredibly hard to solve optimally as the number of cities grows. It's what's called an NP-hard problem. The complexity explodes. Logistics companies face versions of this every single day with delivery routes. Quantum optimization algorithms like QAOA are believed to be well-suited for tackling these kinds of combinatorial problems. They can explore many routes concurrently.
So, finding much more efficient routes for delivery fleets.
Potentially, yes. Minimizing fuel consumption, cutting down travel time, reducing operational costs significantly. Imagine optimizing routes for thousands of vehicles across a country or even globally. Companies like DHL and FedEx are already partnering with quantum computing firms to explore this. Demonstrations have shown potential for improving schedules and reducing transit times.
And less fuel means lower emissions too, right?
Absolutely. Better route optimization has a direct environmental benefit, reducing the carbon footprint of logistics, which is crucial for meeting climate goals.
Okay, optimizing routes is one thing. What about managing the stuff being shipped? Inventory management.
That's the other side of the coin, yes. Efficiently managing inventory is crucial. Holding too much stock ties up capital and risks waste. Holding too little means lost sales and unhappy customers. Predicting demand accurately is key, but it's hard. You need to analyze historical sales, market trends, seasonality, economic factors, even weather. Vast amounts of complex data.
And classical methods struggle with that complexity.
They do their best. But quantum machine learning algorithms, again, things like QSVM or maybe quantum neural networks, could potentially identify more subtle patterns and correlations in that data. This could lead to much more accurate demand forecasting.
Like a retailer knowing exactly how much stock to have for a holiday sale without guessing.
Precisely. Or a manufacturer synchronizing inventory perfectly across multiple global factories to avoid production bottlenecks. It's about dynamically adjusting stock levels in real time for maximum efficiency, minimal waste, and optimal availability.
It seems like optimization is a running theme here. Let's talk about building things, material science, creating new materials.
Yes, and this is where quantum computing's ability to simulate quantum systems truly shines. Discovering new materials with specific desired properties, stronger, lighter, better conductors, catalysts, is fundamental to technological progress. But traditionally, it's been very slow and expensive. A lot of painstaking lab work, mixing things together and seeing what happens. Classical computers can help simulate materials, but accurately modeling the quantum behavior of electrons, which dictates a material's properties, is extremely computationally demanding for complex systems.
Because materials are quantum systems at their core.
Exactly. So quantum computers are naturally suited to simulating them. Algorithms like VuQE and QPE allow scientists to calculate the electronic structure and properties of materials with much higher precision. This could massively accelerate the discovery of advanced materials. Think about materials for better batteries, more efficient solar cells, maybe even room temperature superconductors, which would revolutionize energy transmission, or new catalysts for greener chemical processes.
Are companies already working on this?
Oh yes, tech giants like IBM, Google, Microsoft, as well as chemical companies and research labs are actively applying quantum algorithms to material science problems. It's a very active area.
And does this apply at the super small scale too? Nanotechnology?
Absolutely. Designing materials atom by atom, which is what nanotechnology often involves, requires exquisite control and understanding of quantum effects. Quantum computing can model these atomic arrangements and predict their resulting properties with far greater accuracy than classical methods. This could enable the design of tailored nanomaterials for specific applications, maybe highly targeted drug delivery systems in medicine, or ultrasensitive diagnostic sensors, or materials for next-generation electronics, faster and smaller transistors.
Building from the atom up, guided by quantum simulation. Incredible. Let's stick with energy for a moment. Power grids can quantum help optimize those complex networks.
Yes, managing national or even regional power grids is another massive optimization challenge. You have fluctuating supply from different sources, including intermittent renewables like solar and wind, changing demand, and the physical constraints of the grid infrastructure. The goal is to balance load, minimize energy loss during transmission, ensure stability, and prevent blackouts. Classical methods struggle to do this optimally in real time for very large, complex grids.
And quantum optimization algorithms, QAOA again.
QAOA is definitely a candidate, yes. They could potentially find better ways to route power flow, decide when and where to store energy in grid-scale batteries, or optimally integrate renewable sources. This is becoming increasingly critical as we add more solar and wind power, which aren't constantly available. Quantum could help manage that intermittency much more effectively, reducing reliance on fossil fuel backup generators. It can also help plan grid maintenance and expansion more effectively.
Making the grid more efficient, reliable, and greener.
That's the potential, yes.
Okay. And what about the ultimate energy dream, nuclear fusion? The Holy Grail, as it's often called.
Fusion. The promise of clean, virtually limitless energy by mimicking the process that powers the sun. It's an incredibly difficult scientific and engineering challenge. One of the biggest hurdles is controlling the superheated plasma, the state of matter inside a fusion reactor under extreme temperatures and pressures. Understanding and predicting plasma behavior involves modeling very complex quantum interactions between particles.
Which is, again, extremely hard for classical computers.
Extremely hard. Quantum computers, however, are ideally suited to simulating these quantum systems. They could provide much more accurate models of plasma physics and particle interactions within reactors like tokamaks or stellarators.
Helping scientists design better reactors, optimize their operation.
Exactly. By providing deeper insights into the fundamental processes, quantum computing could significantly accelerate progress towards achieving sustained, controlled fusion power. Major international projects like ITER are already looking at how quantum computing might help them overcome some of the huge challenges they face. It's a long-term prospect, but quantum could be a key enabling technology.
Wow. From energy to materials. Let's look at the planet itself. Climate modeling and environmental science. How can quantum help there?
Climate modeling is another area dealing with immense complexity. The Earth's climate system involves intricate interactions between the atmosphere, oceans, ice, land, and biosphere across many different scales. Building accurate models that can predict future climate change or even make better long-range weather forecasts is computationally very demanding. Classical supercomputers do an amazing job, but there are still limitations.
Can quantum models be more accurate or faster?
The hope is that quantum algorithms, perhaps using techniques like quantum Monte Carlo methods or quantum machine learning, could process the vast amounts of environmental data more efficiently and maybe capture some of the complex dynamics more accurately. This could lead to more precise predictions, say, better forecasting of hurricane paths and intensities, giving more time for preparation, or improved seasonal climate forecasts, which would be invaluable for agriculture and water resource management.
Real-time analysis of sensor data, too.
Yes. Imagine continuously feeding data from satellites, ocean buoys, weather stations into quantum models for dynamic updates. It could lead to a much more responsive understanding of our planet's systems.
Okay, and what about actively fixing environmental problems, like carbon capture?
Carbon capture and storage, CCS, is seen as a potentially vital technology for mitigating climate change, especially for industries that are hard to decarbonize completely. But it relies on finding materials that can efficiently and selectively capture CO2 from emission sources. Designing these materials, things like metal organic frameworks, MOFs, requires understanding how they interact with CO2 molecules at the quantum level.
And again, that's a simulation job for quantum computers.
Precisely. Using algorithms like VQE or QPE, researchers can simulate potential capture materials with high accuracy, predicting how well they'll bind CO2 without having to synthesize and test every single possibility in the lab. This could dramatically speed up the discovery and optimization of better, cheaper CCS materials, reducing the need for expensive trial and error experiments and supporting the transition to more sustainable industrial processes.
It really feels like quantum simulation is a key theme across so many of these applications.
It absolutely is. Simulating quantum systems is something quantum computers are inherently good at, and it unlocks progress in fields that have been bottlenecked by classical computation limits.
Okay, let's bring this closer to maybe national interests. Government and defense. How is quantum computing viewed in that sphere?
Governments worldwide see quantum computing as a technology with profound strategic implications, impacting both national security and economic competitiveness. On the intelligence side, we've already discussed the threat quantum poses to classical encryption. The ability to potentially break adversaries' codes using Shor's algorithm is obviously very attractive from an offensive intelligence perspective.
But that means their codes are vulnerable too.
Exactly. It cuts both ways, which is why there's also a massive defensive push. Governments are investing heavily in developing and deploying quantum-resistant cryptography and quantum communication networks, like QKD. Making sure their own sensitive communications remain secure in a quantum future is paramount. China's QUSS satellite demonstrated a clear strategic intent in this area, achieving secure quantum key distribution from space.
So code breaking and secure communications. What else?
Simulation again, but for strategic purposes. Quantum computers could potentially model incredibly complex systems relevant to national security. For instance, simulating the spread of pandemics or biological threats, analyzing complex economic systems to predict the impact of sanctions or trade policies, optimizing military logistics and supply chains during crises. Think of that traveling salesman problem again, but ensuring delivery of critical military supplies under pressure.
And modeling actual conflict scenarios.
That's another potential application. Modeling battlefield dynamics, factoring in terrain, troop movements, sensor data, potential enemy actions to evaluate different strategies and predict outcomes with greater fidelity than classical simulations allow. It could also accelerate the design of advanced defense technologies, new stealth materials, more sophisticated autonomous drones or vehicles, next-generation sensor systems, all through highly accurate quantum simulation. It's definitely seen as a potential force multiplier.
A new technological arms race, in a sense.
There are certainly elements of that, yes. A race for quantum supremacy and its perceived advantages.
Okay, let's go from global security to the biggest picture of all the universe. Astronomy and space exploration. How could quantum help us understand the cosmos?
Cosmology, the study of the universe's origin and evolution, tackles some of the most fundamental questions we can ask. And many of these questions involve extreme physics and quantum phenomena. Quantum computers could potentially simulate conditions in the very early universe right after the Big Bang, modeling the behavior of fundamental particles and fields under conditions of incredible energy and density that we can't replicate experimentally.
Like simulating the Big Bang itself.
Getting closer to it, yes. Using algorithms like VQE and QPE to study quantum fields and gauge symmetries could help scientists explore mysteries like why there's more matter than antimatter in the universe, or the nature of the primordial plasma that filled the early cosmos. It could also help us investigate the nature of dark matter and dark energy, these mysterious components that make up about 95% of the universe but we barely understand, or analyze the faint patterns in the cosmic microwave background radiation, the afterglow of the Big Bang, using quantum machine learning to extract subtle clues about the universe's infancy.
Wow. Using quantum to understand the quantum origins of everything.
It's a fascinating prospect. And then there's the more practical side of space exploration.
Building better rockets, better probes.
Essentially, yes. Designing spacecraft for long, arduous missions to Mars, to the outer planets, maybe even beyond, is incredibly challenging. Components need to be lightweight, incredibly reliable, radiation-hardened, energy-efficient. Quantum simulations can help design better materials for spacecraft structures, more effective radiation shielding, more efficient solar panels or batteries or fuel cells, and even optimize advanced propulsion systems like ion thrusters or plasma engines.
And AI on board.
Quantum-enhanced AI could play a huge role in autonomous systems for spacecraft, enabling real-time navigation, intelligent decision-making, and efficient resource management for probes that are millions of miles away, where direct human control is impossible due to communication delays.
So NASA, ESS, private companies like SpaceX, are they looking into this?
Yes, space agencies and private space companies are actively exploring how quantum computing could be integrated into mission planning, spacecraft design, and ensuring the reliability of complex systems for future, more ambitious exploration goals. It could really help push the boundaries of where we can go and what we can do in space.
It's truly mind-boggling, the range of potential impact here, from the smallest particle to the largest structures in the universe.
It really touches almost every field of science and technology.
Okay, so we've talked a lot about the promise, the amazing applications. But if we connect this back to the bigger picture, what are the broader societal and economic implications? Because these applications don't happen in a vacuum, right? They're going to cause ripples, maybe even waves.
That's exactly right. The applications we've discussed are not just technical feats. They carry profound implications for society, the economy, security, everything. Let's start with cybersecurity again, because the disruption there is so fundamental. As we said, traditional encryption like RSA and ECC faces obsolescence. This isn't a minor issue. It necessitates a global overhaul.
A global scramble for quantum-resistant algorithms, as some sources put it.
Precisely. Governments, banks, tech companies, military organizations, everyone needs to transition their systems. And that's a massive undertaking. Think about the challenges. Ensuring the new quantum-safe algorithms are truly secure and properly implemented, making them work seamlessly with existing systems, interoperability, the sheer cost of upgrading potentially billions of devices and systems worldwide, and the need to train people and raise awareness. It's monumental.
The risk, if we don't transition fast enough, your data, my data, everyone's data.
Your personal data, financial records, health information, corporate secrets, government communications, all potentially exposed if encrypted with vulnerable algorithms. That store now, decrypt, later's threat looms large. The urgency is very real.
Okay, so cybersecurity is facing a massive upheaval. What about the economy more broadly? Will there be winners and losers?
Inevitably, yes. Major economic shifts are almost certain. Companies and even entire industries that fail to adapt to the quantum era might lose their competitive edge, potentially very quickly.
Can you give some examples?
Well, think about financial services. If some firms can optimize portfolios or assess risk dramatically faster using quantum, others using classical methods might struggle to compete. In healthcare, companies that leverage quantum for faster drug discovery could leave slower innovators behind. Manufacturing and logistics firms that don't adopt quantum optimization might face higher costs and slower delivery times than competitors who do. Energy companies unable to optimize grid management or discover new materials could become less efficient.
So adapt or risk falling behind.
That's often the dynamic with disruptive technologies. But it's not just about risk. This disruption also creates entirely new economic opportunities, new industries. We're already seeing this happen. Companies dedicated to building quantum hardware, different types, like superconducting qubits, trapped ions, photonic systems. A whole ecosystem is emerging. Then there's the quantum software layer, developing the algorithms, programming languages, libraries, and applications needed to actually use these machines effectively.
And ways for people to access quantum computing without buying one.
Exactly. Quantum as a service, or CODES, is becoming huge. Cloud providers like IBM, Google, Microsoft, Amazon Web Services, and others are offering access to their quantum processors over the internet. This democratizes access, allowing researchers and companies to experiment without needing their own multi-million-dollar quantum computer.
And the security aspect creates its own industry, too.
Absolutely. The whole field of post-quantum cryptography, developing those new quantum-resistant algorithms, is booming. And companies offering QKD systems and other quantum security solutions represent another growing market sector. So new industries are definitely being born.
Okay, new industries, old industries disrupted. What does this mean for jobs, the job market?
That's a critical question and likely a complex picture. On one hand, quantum-powered AI and optimization could automate tasks previously done by humans, even highly skilled cognitive tasks. We might see automation increase in areas like manufacturing, logistics, data analysis, financial trading, even aspects of medical diagnosis or legal research. This could lead to job displacement in certain roles.
What kinds of roles might be most at risk?
Potentially routine cognitive tasks, certain types of data processing, bookkeeping, some forms of manual labor that become more easily automated with smarter systems, possibly even some analytical roles where quantum AI can outperform humans in speed and complexity.
But automation usually creates new jobs too, doesn't it?
Historically, yes. And quantum computing will certainly create new, high-skilled jobs. We'll need quantum physicists, quantum computer engineers, algorithm developers, quantum software engineers, specialists in quantum machine learning, quantum security experts. Entirely new career paths are opening up. The challenge is the transition. There will be a critical need for workforce reskilling and upskilling. People will need strong digital literacy, advanced technical training for these new roles. And interestingly, there might be an increased value placed on uniquely human skills. Creativity, critical thinking, complex problem solving, emotional intelligence, collaboration, things that AI, even quantum AI, may struggle to replicate.
But this transition could be difficult for many people. It raises questions about inequality, doesn't it?
It absolutely does. If the benefits and new jobs concentrate among a highly skilled elite while others face displacement, it could worsen economic inequality. This brings up the need for societal frameworks, education reforms, social safety nets, lifelong learning initiatives to support workers through this potentially turbulent period.
And these shifts aren't just economic, they have geopolitical dimensions too, right? You mentioned the race for quantum supremacy earlier.
Yes, the geopolitical implications are significant. Whichever nations lead in developing and deploying quantum technology could gain substantial advantages.
Advantages in what? Intelligence, military, economy.
All of the above. Intelligence gathering through code breaking, enhanced military simulation and technology design, significant economic boosts from dominating new quantum industries or optimizing existing ones. It's seen as strategically vital. That's why we see this intense global competition. The US, China, the EU, Canada, UK, others pouring billions into research and development. It really does resemble the space race or the nuclear race in some ways.
Is it all competition or is there collaboration too?
It's a mix. There's open scientific collaboration on fundamental research, which is healthy. But there's also fierce competition, particularly around developing deployable hardware, specific algorithms with commercial or military value, and setting global standards. This dynamic could potentially shift global power balances, create new alliances, and introduce new tensions, especially around cybersecurity and technology access. Technology diplomacy around quantum is becoming a real factor in international relations.
With all this power, economic, military, computational, comes the potential for misuse, or at least unintended negative consequences. What about inequality and ethical concerns?
This is hugely important. If quantum computing resources, the hardware, the expertise become concentrated in the hands of just a few wealthy nations or giant corporations, it could massively exacerbate existing global inequalities.
A quantum divide.
Exactly. A quantum divide where richer nations pull even further ahead, leveraging quantum for economic growth, scientific discovery, and healthcare advances, while developing nations are left behind, unable to access or afford these transformative capabilities. This could lead to greater economic disparities, potentially political instability, and unequal access to things like quantum-driven medical breakthroughs.
And beyond access, what about ethical challenges and how the technology is used?
Several major concerns. We've talked about the surveillance potential if encryption breaks down a massive threat to privacy and civil liberties worldwide. Then there's the issue of quantum-enhanced AI. If these systems become incredibly powerful and complex, their decision-making processes might become opaque, like a black box. How do we ensure accountability? How do we prevent or detect bias in quantum AI systems used for critical decisions like loan applications, hiring, parole hearings, or even autonomous weapons systems?
Transparency and bias are already big issues with AI. Quantum could amplify them.
It could, yes. And we have to remember quantum computing is a powerful dual-use technology. It can be used for immense good curing diseases, developing clean energy, but also potentially for harm, creating new weapons, enabling more sophisticated cybercrime or state-sponsored attacks.
So what's the answer? How do we navigate these ethical minefields?
It requires a proactive global effort. We need robust governance frameworks, international agreements, ethical guidelines developed through open discussion involving scientists, policymakers, ethicists, and the public. Public awareness and education are crucial so that society can make informed decisions about how this powerful technology should be developed and deployed. It's not just a technical challenge, it's a societal one.
One last area of societal impact, the environment. We talked about how quantum can help climate change modeling, materials, renewables. But does quantum computing itself have an environmental footprint?
That's a really important and often overlooked question. There's a dual nature here, too. While quantum offers tools to fight climate change, the computers themselves can be quite energy intensive.
Why is that?
Many leading quantum computing approaches, like those using superconducting qubits, require cooling down to extremely low temperatures, close to absolute zero. Those cryogenic cooling systems consume a lot of electricity. The specialized facilities housing them also have significant energy demands. If that energy isn't coming from clean, renewable sources, then quantum computing itself could contribute to carbon emissions.
Are there other environmental concerns, like the materials used?
Yes, building quantum computers often relies on specialized materials, some of which might involve rare earth elements or complex fabrication processes with their own environmental impacts related to mining, resource depletion, and waste generation. And then there's the issue of e-waste. As the technology rapidly evolves, older quantum hardware will become obsolete. We need sustainable plans for recycling or disposing of this complex equipment responsibly.
So we need to be mindful of the life cycle impact.
Absolutely. There's a growing focus on developing more energy-efficient quantum architectures, using sustainable materials, and designing for recyclability. Ensuring the quest for quantum advantage doesn't inadvertently worsen the environmental problems we're trying to solve with it requires careful planning, responsible resource management, and supportive policies.
Okay, so we've covered the applications, the societal shifts, the risks. Let's zoom out one last time. Some sources suggest quantum computing won't just disrupt industries. It could fundamentally upend the world in ways that sound almost like science fiction. What are some of those ultimate transformations?
Right, we're moving into territory that's more speculative but rooted in the potential trajectory of the technology. One concept that often comes up is the connection between quantum computing and the technological singularity.
The singularity, the idea that AI development could hit a runaway feedback loop, rapidly surpassing human intelligence.
Exactly. The argument is that quantum computing's immense processing power could dramatically accelerate AI research and development. If quantum computers can train vastly more complex AI models or explore entirely new AI architectures much faster, it might push us closer to that point of uncontrollable exponential AI self-improvement.
Redefining what machines can do, blurring the lines with human cognition.
Potentially. It could enable AI systems to explore paradigms of intelligence we haven't even conceived of. Of course, this brings all the societal implications we discussed, job displacement, ethical quandaries about control and bias, security risks into even sharper focus. It's a profound unknown.
Another upending scenario seems to revolve around that security breakdown we discussed. What if it happens suddenly?
That's the nightmare scenario for cybersecurity experts. A sudden, unexpected arrival of a large-scale, fault-tolerant quantum computer capable of breaking current encryption before robust quantum-resistant systems are universally deployed could indeed cause chaos.
Chaos how? What would actually happen?
Imagine global communications becoming insecure overnight. Financial transactions compromised, secure websites breached, critical infrastructure systems, power grids, water supplies, transportation networks, healthcare systems that rely on encrypted communication potentially vulnerable to disruption or attack. It would undermine trust in the entire digital ecosystem.
A complete paradigm shift in what secure means, happening almost instantly.
Yes, it underscores why the proactive, albeit challenging, transition to post-quantum cryptography is so absolutely critical. We need to be ready before that potential breakdown occurs.
And economically, you mentioned winners and losers. Could this lead to a truly radical redistribution of global wealth and power?
It's a significant risk. If the benefits of quantum computing accrue primarily to the early adopters, likely wealthy nations and large corporations, it could dramatically widen the gap between the quantum haves and quantum have-nots. We could see a world where a few entities dominate key industries globally, leveraging quantum advantage to consolidate economic and political power to an unprecedented degree.
Worsening global inequality on a massive scale.
It's a very real concern. Ensuring more equitable development and access is perhaps one of the biggest non-technical challenges facing the quantum era. How do we democratize access through things like open source initiatives, affordable costs, global education programs? How do we ensure quantum is used partly for social good, addressing global challenges like poverty or disease in developing nations, not just for profit and power consolidation?
But amidst these daunting challenges, there's also the potential for incredible good, right? You mentioned a scientific renaissance.
Absolutely. On the flip side of the risks is the immense positive potential. Quantum computing could be the key that unlocks solutions to some of science's longest-standing, most fundamental unsolved problems. Problems in physics, understanding quantum gravity, the nature of space-time, the fundamental forces. Problems in chemistry, designing perfect catalysts, understanding complex reactions. Biology, fully cracking protein folding, understanding the origins of life, revolutionizing genomics. Environmental science, truly accurate climate models. New energy sources, solutions for pollution.
Ushering in a whole new era of discovery and innovation.
Exactly. A period of rapid advancement across multiple fields, leading to technologies we can barely imagine today. Advanced manufacturing, truly intelligent AI, maybe even capabilities that make interstellar travel feasible someday. It could be a profoundly transformative period for human knowledge and capability.
And maybe closer to home, how might it change our cities? Urban development.
That's another fascinating area. Quantum computing could enable much smarter urban planning and management. Think about using quantum optimization to design truly efficient public transportation networks, manage traffic flow in real time to eliminate congestion, or coordinate autonomous vehicle fleets seamlessly. Or optimizing the allocation of city resources, energy distribution block by block, water management systems, waste collection routes for maximum efficiency and sustainability.
Simulating city growth or the impact of new infrastructure projects before they're built.
Precisely. Modeling complex urban dynamics to make better decisions about land use, zoning, and preparing for challenges like climate change impacts, designing cities that are more resilient to heat waves or flooding. It could also lead to more data-driven and even more participatory urban governance, allowing citizens to better understand and contribute to planning decisions. Smarter cities in the truest sense.
So we've covered a huge amount of ground. From qubits to cosmology, from encryption to ethics, it's clear quantum computing isn't just another incremental step. It feels different. We've seen it's definitely a double-edged sword, as you said. On one side, this incredible potential for innovation for solving huge problems. On the other, significant risks, security breakdown, economic disruption, inequality, ethical dilemmas.
It really is. And this raises perhaps the most important question. How do we, as a global society, navigate this? How do we ensure this incredibly powerful technology is harnessed responsibly? It's not going to be easy. It demands robust governance, probably new forms of international cooperation, and, crucially, broad public understanding and engagement. We need foresight, careful planning, and a constant effort to balance the drive for innovation with the principles of equity, safety, ethics, and sustainability.
It's not just up to the scientists and tech companies, then.
Absolutely not. It requires input from policymakers, ethicists, social scientists, educators, and the public at large to shape the trajectory and ensure the benefits are widely shared and the risks are proactively managed.
So, wrapping this up, what does this all mean for you, listening right now? As we stand here, really at the dawn of this quantum era, what's our collective responsibility? How do we shape a future where this immense power actually serves all of humanity, not just a privileged few? And maybe just as importantly, how quickly can we adapt our understanding, our infrastructure, our institutions, to keep pace with a technology that seems poised to change the world at, well, quantum speed?